The first notebook we're going to look at is the Technology Guide on Superconducting Qubits, Improving the Performance of Single Qubit Gates. This notebook is a great introduction to Q-Control's optimization tools and shows you how to generate pulses that are robust to noise processes that affect real quantum hardware. The pulses that are generated are actually demonstrated on IBM superconducting devices using their special format OpenPulse, and we show in which way they are robust and the quality of their performance. The first thing we're going to do in this notebook is create an optimized pulse that achieves a NOT gate. To start, we have to write down a Hamiltonian that describes our system. In this case, we are considering a superconducting qubit driven by a microwave drive with IQ modulation. So our control Hamiltonian has an I channel coupled with a sigma X operator and a Q channel coupled through a sigma Y operator. The noise process we're going to consider first is a dephasing process. So we are also going to have a term in the Hamiltonian with a slow varying sigma X operator. When I say slow varying, I mean slow varying compared to the Rabi rate. The Hamiltonian also happens to include a control error. This is some error which happens to occur on the microwave drive. But to begin with, we're going to consider this as 0 and just look at the dephasing process. To do an optimization with the Q-Control package, you first have to let us know about your system. So you define your series of sigma operators, and then you create a series of controls, noises, and finally the target you want. We are actually going to optimize 2 pulses. So we create our I and Q channels, but we create one where we do not have any limits on the bandwidth. So all we do is limit the total maximum Rabi rate that the pulse can achieve. Then we create another pulse, which has a maximum slew rate. This bounds the difference between each of the segments in our pulse, effectively creating a bandwidth limit. You will see later on that by having 2 pulses, we can investigate which ones are better implemented on real hardware. Lastly, we define a target. So we simply select the unitary that we want to achieve. In all cases, you can actually define arbitrary controls, arbitrary Hamiltonians, and arbitrary noises. Running the optimization itself is just one line. We simply call Q-Control services robust optimization. This then sends a bunch of information up into our servers. A series of servers are spun up simultaneously, which solve the optimization much faster than a local instance. Then this information is returned to you. You then get a series of pulses, which you can program into your quantum computer. Here we're showing you the unconstrained result. As you can see, it does change quite rapidly between each segment. The bound slew result, on the other hand, changes much more slowly, effectively making a band limit. And we finally present a square pulse just as a comparison, so we can compare different cases. Now that we have these robust pulses, the question is, do they achieve the correct operation, and in what way are they robust? Q-Control also provides a variety of tools for investigating these questions. We first consider a simulation of the dynamics of these pulses. I won't go into the details here. You can check the feature guides if you want the exact syntax. But basically, we run a simulation of each of these pulses as a function of time. We're going to assume that the qubit is each initialized in a ground state, and then in the ideal scenario, when a NOT gate is achieved, we'd expect that all of the excitation will go from the ground state to the excited state. As you can see here, all 3 of our pulses achieve that aim when there is no noise. The unconstrained, bound slew, and square all finish with excitation all in the 1 state. The next set of tools allow you to investigate the robustness of these pulses. We present 2 tools available from Q-Control's package. The first is the filter function. The filter function gives you an understanding of how the infidelity is affected by a noise process as a function of frequency. Here we can see both the unconstrained and bound slew controls strongly suppress low frequency noise, as the filter function has a very small value for low frequencies. The square pulse, on the other hand, is flat across all of the low frequency band, indicating that it will let any low frequency noise through and have a negative effect on the infidelity. We also provide a quasi-static robustness scan. This gives you an understanding of the robustness of a control as a function of the size of the noise process. We assume that the noise process is effectively stationary, then we do a series of Schrodinger integrations. Here we can see that all 3 controls achieve the correct operation when the detuning error is 0. But as we increase the detuning error, we can see that the square pulse rapidly increases the infidelity, which is equivalent to basically the ground state population at the end. The unconstrained and bound slew solutions remain flat, showing that they are robust to this noise process. Now that we have our optimized pulses and we have confirmed that they do the correct NOT operation and are robust to the dephasing process, we can implement them on real hardware. Here we implement them on IBM Q's device using their open pulse format. In open pulse, you do not directly control the Rabi rate of the qubits. Instead, you use a dimensionless number between 0 and 1, which is proportional to the microwave drive. So in order to map the values that come out of Q-Control's optimized package to the real values you want to program in open pulse, we have to do a series of calibration routines. Essentially, we do a set of Rabi experiments where we set a fixed voltage height, and then we increase the duration. This is repeated multiple times, and with each time, we fit the Rabi rate at each point. We then get this calibration curve that gives us the relationship between the voltage that you program in IBM's open pulse format and the actual Rabi rate, which you can translate from the Q-Control's open package. Here you can see that for the most part, it is a quasi-linear relationship. It just becomes nonlinear for high voltages. Hence, we set a maximum Rabi rate, which doesn't get into that nonlinear regime. Now that we're able to translate the pulses from Q-Control's package to the IBM open pulse format, we can run a series of experiments. First, we're going to investigate which pulses were implemented the best. We do a series of experiments where we compare the state of the qubits to the simulation results as a function of time. Here we can see the square result does what we expected. It's basically half a Rabi oscillation. At the end, there is a slight divergence between the experimental results and the simulation, and this is due to a span error in the measurement. The bound-slew pulse also appears to be implemented quite well, and you can see that the final state is comparable to the square case. The unconstrained pulse, on the other hand, does not appear to be implemented correctly, and we can see at the end there is a significant divergence in the final state that is measured on the device compared to the simulation. This shows that by taking into account real physical constraints like a bound slew, Q-Control's package can create pulses that are better suited when implemented on real hardware. We can also experimentally verify the robustness of these pulses. We do so by replicating that quasi-static scan I presented earlier. Here we can see when there is no error process and the detuning is 0, both the square pulse and the bound slew produce the correct result. Both of them show that at the end of the operation, the ground state population is 0 as expected. As we increase the error and increase the detuning, we can see that the square pulse rapidly diverges from the ideal operation, showing it is not robust to this noise process. The bound slew result, on the other hand, has a flat curve, indicating that it is robust to the detuning error as we designed it. Once again, the unconstrained pulse doesn't appear to apply the correct operation, whether we have noise or no noise. As a comparator, we also provide IBM's default X gate, and we can see that this is not robust to this dephasing error. We have also independently measured the amount of drift on the qubit as a function of time over the day. We typically see drifts up to 0.25 megahertz. This indicates that if you used Q-Control's pulses for X gates, your algorithms would run more accurately for longer during the day. We are continuing to work on further results on randomized benchmarking and homogenization of errors across the chip. Stay tuned for more results from Q-Control on those topics. The technology guides also provide a variety of other examples showing how to make robust pulses to common noise processes in real quantum devices. I'll briefly show you a result of a quasi-static scan of a pulse that has been designed to be robust to amplitude noise. This occurs when you have noise that you may have noise on your microwave drive due to a miscalibration between your Rabi rate and your expected value. Once again, we can see that the square pulse when run on IBM quickly diverges from an ideal operation as you add control amplitude error, while the bound slew remains robust. And finally, once again, we see that our unconstrained one is not implemented well on the machine. Q-Control's optimized pulses have also been verified experimentally with cold ion experiments. In the technology guide, Cold Ions Improving the Performance of Single Qubit Gates, experimental results gathered at the University of Sydney and Michael Biersich's lab are presented. Here you can see a primitive pulse is compared to a Q-Control optimized pulse, which is robust to both amplitude errors and dephasing errors. Here we can see that the Q-Control's optimized pulse remains robust to error as it is increased compared to this primitive pulse. If you're interested in any of the technical details behind this optimization tool or any of the features in Boulder Opal, I highly recommend that you go to the archive and look at our manuscript, Software Tools for Quantum Control, Improving Quantum Computer Performance Through Noise and Error Suppression. We also provide a benchmark and head-to-head comparison of our optimization tool compared to a naive implementation with NumPy and Qtip. Our package is able to beat the naive implementation by almost a factor of 100 and Qtip by almost a factor of 10.